Okay, today we will start another wave topic, a wavelength and the angular wave number. We will talk about little bit period and the angular frequency and the frequency. We will also discuss today the speed of a traveling wave. So, going through the first topic under the waves, that is wavelength and angular wave number. Wavelength and angular wave number. So, the wavelength lambda of a wave is the distance that is parallel to the direction of a wave propagation between the consecutive repetitions of the shape of the wave, and it is the minimum distance between two consecutive troughs and crests or two consecutive points in the same phase of a wave motion. So here we have a complete definition of wavelength, that it is a minimum distance between the two consecutive troughs, or it may be crest also, or this may be a minimum distance between two consecutive points having same phase of direction. So if we denote the wavelength via lambda, if we denote the wavelength 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 by lambda, then it may be defined as it may be defined as first the minimum distance between two consecutive between two consecutive troughs, or we can say the minimum distance between two consecutive crests, or in other words we can say the minimum distance between two particles of same medium in same phase in same phase in same phase wave motion. Now a typical wavelength is marked in a figure 15.6. We already discussed about that. Let us suppose if this will be a on x-axis we have time component, on y-axis we have displacement component, then if the wave motion will be shown by this way, that is a sinusoidal wave, then here we have crest and here we have troughs. This will be the amplitude, that will be the maximum distance of a particle from its mean position. So this will be lambda in this case, and this will be also lambda for this same wave. Now if we have two particles in the same phase like this, then again this will also be shown as a lambda. Now in this wave for t equals to 0 and phi equals to 0, at the time the equation reduces to 0 at t equals to 0 and phi equals to 0. The equation yxt, here a is for amplitude and this will be sine component, kx minus omega t plus phi. This will be an angular wave number. We already discussed about that. Now in this equation, if we put t equals to 0 and phi equals to 0, the equation reduces to the y x0 and a sine kx. Now by definition the displacement y is same at both the ends of this wavelength, so that is at x equals to 1 and x equals to x1 plus lambda. By the definition, displacement y is same at ends both the ends of this wavelength, this value, that is at x equals to x1 and x equals to x1 plus lambda. So again from equation 1, again from equation 1 we have, or the equation 1 becomes reduced into the a sine kx1, a sine kx1 plus lambda. This reduces to a sine kx1 plus k lambda. This condition can be satisfied only when this condition can be satisfied only when k lambda equals to 2 pi n, where n equals to 1, 2, 3. Since lambda is defined as the least distance between points with the same phase. It's least distance between the points having same phase. N equals to 1 and n equals to 1 and lambda equals to 2 pi upon k, or k equals to 2 pi upon lambda. Here k is called the propagation constant or the angular wave number. Here k is called the propagation constant or the angular wave number. Its SI unit is radian per meter. Its SI unit is radian per meter or radian meter inverse. That is of both same thing. SI unit is radian per meter or radian meter inverse. Now, period, angular frequency and frequency. Period, angular frequency and frequency. Now, the figure shows the graph of the displacement y of equation 15.2 versus time t at a certain position along the string taken to be x equals to 0. Now if you monitor the string, we would see the waveform in such a way like this. So suppose this will be a displacement axis, this will be a time axis, then the wavefront travel along the axis like this. So here we clearly know as this will be amplitude A, this will be a time period, this will be a time axis, and this will be a displacement axis. Here we can see that both these particles of the same wave are in same phase along with the wave motion. Now this will be a figure where a graph of a displacement of a string t, a graph of the displacement of element at x equals to 0 as a function of time, as a function of time, as a function of time, as a sinusoidal wave. Thank you, and that's it for today.